Alright, in this video I'll be going over pistons, how to design with pistons, and how do you calculate how much force you'll need, how do you pick a piston, how should you be mounting it, stuff like that. So here I just have a simple layout sketch of, this white rectangle here could be the drivetrain, so this would be an intake that pivots up. This could be the elevator, it could be the carriage of an elevator, and there's a intake here, or an outtake there that pivots up or down. So, and there's our piston. It's just a rectangle line. You don't need any more detail on it. Now, one thing to remember, like right off the bat with pistons, is you never want to have, like, let's say it's flat, you never want your piston to be like flat like that when you're trying to pull something. The reason for that is, you see how our manipulator is almost flat, like it's basically flat, and the piston rod is also flat. When you try to move this piston to pull back, you're not gonna be able to pivot this mechanism back. Most 90% of the force of that piston is trying to push this pivot point back, rip it off your drivetrain. So never ever mount your pistons like that. This angle between your piston and your mechanism, that should not get close. The moment it gets close, the moment you're going to be giving your piston a really hard time and possibly breaking parts of your robot. So, the ways to get around it is obviously the place where your pivot point is mounted, right? Let me just grab that. Okay. So the place where your pivot point is mounted, that could be further up, right? So you can make like a triangular plate of some sort, trapezoidal plate, and then attach your piston there. That will work because now you see how the piston is away from here and it has an angle on your mechanism. Or another solution for it, you just take the back of your piston and mount it higher up like that, and then you get a great angle. Right, so I'm just going to attach the piston there. In terms of where this piston rod goes on your manipulator, basically it's like a door. If you try to push your door closed and you're pushing on the hinge, like in this area, you're going to need a lot of power, and it's just hard, right? It's hard to do it because it's right next to the pivot point. If you mount your piston all the way at the edge, it'll be really easy for your piston. You won't need a beefy piston to put it over there. But it also means, one, you're traveling this long arc, so you need a longer piston. And then two, if you're traveling this whole area, you're going to need all that space. There might be other mechanisms there. So you want to stay away from this end, especially because that's how you wreck your robot. That's how you need a beefy piston. And you want to try to be in this area, and you rarely might need to be at the very edge. Now, the physics, or how you want to figure out like how much force you need, basically it depends on where the weight is on your mechanism here and relative to that pivot point. So obviously if you have a weight and you hold it right next to your body and you try to lift it up or down, it's fairly easy because it's right next to the pivot point. But if you stretch your hands out and you try to lift something, it's a lot harder. Same thing goes here. If you have motors, gears, chain, wheels, all of that, and it's concentrated around the far edge away from the pivot point, it's going to be a lot harder to lift this versus if it's mainly concentrated around the pivot point. So that's something you want to keep in mind. Now for this example, since our pivot point is 1 inch away from the edge and this whole thing 7 inches long, let's say, so that's 6 inches, right, to the very edge, and let's say we have 6 pounds of weight concentrated around this edge. You can like average out all the weights and figure out how far away it is on average, right? So I'm just going to say 6 inches at the very edge. So our torque, the force required to pivot this thing away from, like, the gravity is pulling down on it, 6 times 6, 36 pound-inches of force, or torque. And we need at least 36 pound-inches of torque to move this thing up. At least. You probably want more. And the way we figure out how much force or how much torque our piston is making depends on how far away our piston is mounted, right? Remember, again, if it's close to the pivot point, it's going to be harder. The further away it is, the better it is. So I'll just make a line between the piston and where it's mounted, or where the pivot point is and where it's mounted. Let's make it a center line so it looks different. Driven dimension, just so you can see what the length is here. Alright, so that's our length there. And then the second thing on how you figure out how much torque your piston's making is the angle between this connecting between the pivot point and your mounting point, and dimension between that and your piston rod. So right now it's like 29.8 degrees. So obviously what it means is if you draw a triangle out, your piston's 100% of its force is going in that direction, that way, right? So you make a triangle, most of the force is trying to go in that direction, and the only way you pivot this mechanism here is if you put a force upwards, not back there. So what I'm trying to say is, if you want to figure out how much torque your piston's making, it depends on the sine of this angle. So the greater this angle is, the more power your piston will have. And that makes sense, because when my mechanism is up here, it should be a lot easier for my piston to just pull on it, because it's just straight up pulling back. Versus when it's over here, it's a lot harder for it. You know, it's equivalent to when you're doing sit-ups, and when you're lying flat, it's a lot harder to be in this region, versus when you're up there, it's super easy to cover this distance here. Now, for pistons, you can find it on McMaster. I have a video on how you can find them and download files and then use them in an assembly and stuff. This is mainly design-based video, so if you scroll down to power transmission, yes, and then if you go on linear motion, actuators, round body or cylinders, this is where they all are. I'll just do a quick overview. So double acting basically means, if you look here, it has two air ports. Those are air ports. They're not for mounting. Please don't mount there. The way you mount a piston is through these mounts over here that you can thread stuff there. But basically what happens with double acting is you can put air into the back port and the piston rod will extend, or you can put air into the front port and the piston will retract. Right, and then with single acting, it's a little bit different. With single acting, you can put an air to the back port and it'll push out, but there's no port in the front, and there's a spring there actually. So the moment you let air go out of here, this rod will go back. And this is useful for applications where you just need to control one part of the motion. You don't care about how it comes back. Like with double acting, you can control when it goes forward and when it comes back a lot better than like single acting. And then the other one that's like used a lot is impact resistant ones, or not a lot, but you can use these basically for applications where pistons are located in a dangerous area, like near the corners of a robot, outside areas where it can get hit by another robot and it can get damaged, right? The pistons, right, any force along these piston rods, like in the direction, like this direction, is fine. They'll take it for the most part. The way you break pistons is if you put a force sideways on them. So if this is mounted like this and the robot comes in and hits the side, that piston's probably going to bend. It's probably not going to work. So keep that in mind. If you're putting pistons near the edge of your robot, you might want to go with impact resistant ones. And to calculate like the numbers for it, I'm just going to use double acting as an example. And there's two vocab words that are important. There's stroke, you already saw here, but what it means is my piston starts off here and I put an air on it and it moves some distance, and the amount of distance that it can move is the stroke. So if I want my flag to move 3 inches away from where it is right now, I need a piston with a stroke of 3 inches. And stroke is different from your piston's actual length, as you can see in this diagram. And then the bore is the inner diameter of your piston, so that's where the air actually is and where the air is, and that inner chamber's diameter. So basically, like, to sum it up in 2 words or few words, the bigger the bore, the more power you'll have. And generally the bigger the stroke gets, the flimsier pistons become, and that's just a rule of thumb with anything. The bigger the longer you stretch like a piece of 2x1, it becomes easier to bend it and it becomes more fragile. So keep that in mind. If you have a really long stroke, you want to make sure that it's protected. It's more prone to breaking if it's super long and it's not like impact resistant or something. Now if you go on the JVN calculator doc, there's actually a section for pneumatics that I added, and then in here basically working pressure 60 pounds per square inch for FRC standard, and then the bore of your piston and the rod diameter, and then the lever arm, the length of the lever arm, and the angle. You'll get that from your layout sketch, and then you get basically your pushing and pulling torque. Now the reason why your pushing and pulling torque are different is because if you look in the diagram, right, again I said the air pushes on inside the piston, and that's what causing the motion. So over here on this port, I have access to the whole internal area of the piston, versus on the front port, because there's a rod going through this front rod, the air actually acts on a little bit less area, which is why your pulling torque is a little bit less. And then if you look at the calculation, all we're doing is we're subtracting the area of this piston rod, the piston rod there. And so going back to our example, 6 pounds, 6 inches away from the pivot point, when it's flat like that, right, 36 pound-inches of torque, we want to have at least that amount if we want to do anything here. So let's say, we're 29.5 degrees, right, that's the angle here. And if you're wondering how you get dimensions with the parentheses, that's just a driven dimension. What that means is I can move my sketch around and the dimension just serves as like a measuring tool almost. It's just a reference. It doesn't actually set this to be some number. So where were we? Yeah, let's go with 29.5 here. 29.5 degrees and 2.7 inches.